Welcome to Advanced Manufacturing Now. Today we're revisiting a conversation from the Advanced Manufacturing Now archives. In this episode, host Bruce Morey speaks with Chuck Somerville of Ceratizit about the 6 keys to successful milling applications. Their discussion covers material selection, part geometry, work holding, machine capabilities, and the importance of aligning tooling and machine strategies to maximize productivity and part quality. We hope you enjoy.
Today's episode is sponsored by our guests.
Hello, and welcome to Advanced Manufacturing Now, the podcast for manufacturing professionals. I'm your host, Bruce Morey, Senior Technical Editor for Manufacturing Engineering Magazine. Our topic today are the 6 keys to a successful milling application. Joining me today to discuss this topic is Chuck Somerville from Ceratizit. Chuck is a tool and die maker by technical training with 10 years in plant manufacturing experience, including industrial engineering. The balance of 30-plus years has been in the technical sales and application of cutting tools and machine tools. In the past 5 years, he has spent much time developing and conducting training of sales engineers and end users on application of cutting tools to get maximum efficiency from the machining process. Welcome to the show, Chuck.
Glad to be here, Bruce. It's an interesting opportunity for me to be involved with you. So thank you very much for the opportunity.
Well, I think our listeners are going to really like it as well. You know, we talked about it at the very beginning in the title. There are 6 keys to successful milling application. Let's start out with the very first, from your perspective. What are the important points a machinist has to be concerned with for successful milling application in today's world?
Well, the key in all cases is, as the machinist, his job is to make his part to print. And the key in making the part to print is to understand all of the factors that can affect and influence the success of that operation. And the first thing always is to consider what is the part made out of and the configuration of that part, which then leads to your ability to hold it and how much machining you have to do to it, and then to go through and assess the overall application as far as your machine and the tooling and stuff that would go into it.
Can we talk a little bit about the variations of material? There is material from, 1020, 1040 mild steel, all the way up to the stainless steels and the super alloys. Just in general, is it as hard today to machine stainless steel as it is something else?
Well, none of the material necessarily is hard to machine per se. It's a matter of understanding what that material is, because you can always change the cutting tool, the cutting parameters to match whatever that material is. It may take you longer to machine it. It may wear tools out faster. But again, as you mentioned, we machine anything from low-carbon 1018 type steel all the way up through hardened tool steels, Inconels, titaniums. It's just a matter of matching the right tool to the application and then setting the right cutting parameters.
And I think that's the point I wanted to make, is that with technology such as available from companies like Ceratizit, you're really not limited by the materials selection that you have available, right? I mean, you can do almost any material you want to do.
We can. It's a matter of if all the other factors we have blend into that, particularly like how well can you hold the part, what kind of tolerances and finishes do you want to achieve, and what is your machine tool that you're going to do it on.
And I'm sure the configuration is just as important. You know, when you talk about configuration, we're also talking about really multi-axis machining. Before there was, 1-axis, 2-axis, 3-axis kinds of machines. Now we're getting into 5 and 6-axis machines. And that allows designers to come up with much more complicated configurations. What advice would you give to a machinist when it comes to these more complicated parts?
Well, one of the things that really contributes to the complicated parts, or even I'm going to say as you were talking about, the multi-axis machines, comes back to I hate to use the term, but the skill level of the shop itself. More and more shops today, they have a programmer, they have a setup operator, they have an operator on the machine, but all too often they all don't share a common knowledge. The programmer knows how to generate code, and the machine operator may know how to load the part in the machine and push the buttons, but the idea in a lot of cases is the programmer doesn't understand what all happens when the operator hits the button and the tools start cutting. And so that's probably one of the bigger things that comes into play, is everybody understanding, even from something as simple as based on the configuration of the part, is tool designers. I think one of the things that's happening in our industry today is that we're at a transition point. An awful lot of people that have the 20, 30, 40 years of experience are retiring, and a lot of companies haven't backfilled to have people that are knowledgeable, because that's the one thing that you cannot give to somebody is experience. That experience comes from doing jobs and learning different ways, because I hate to say it, but a lot of times all the engineering theory in the world is only that. It's only engineering theory, and every application becomes a little different, and you have to understand the idiosyncrasies of the ability to hold the part, and of the machine to machine the part, and of the tool to cut the part.
Reminds me of a phrase I heard when I was a young engineer. In theory, practice and theory are the same, but in practice, it isn't.
That's right. Exactly correct. It's kind of funny. I used to make a joke when I was in the shop as a production supervisor, and I'd get the engineers upset with me because I would make the comment is that you're not an engineer, you're a cartoonist. You make funny pictures on paper, and you don't have the full understanding of what it is. You put something down on paper, but we may not have the capability within our facility to hold the part or machine the part because we don't have the right equipment. So
Right.
a lot of times that becomes a real challenge.
Well, this is one of my first possibly naive questions, but when I think of programming, I think of generating tool paths, right? I mean, you get a camera
true.
model in, you get a really smart person to sit down and figure out the most efficient way of taking material off. But how does that translate? This is my question: is how does that translate into actual tooling, where the tool cuts the material? I mean, how do you pick the right tool to make that tool path?
Well, and that's exactly where you have to start looking at all the other parameters involved in it, much like we talked about the transition of experience. The other thing is the ability to hold the part. If you don't have somebody who has a good knowledge of fixture design, and depending on, are you making one part or are you making thousands of parts? Because if you're doing one part, you can figure out a simplified way of holding the part and very cautiously go about the machining process. Where if you're going to make thousands of parts, you want to be as efficient as possible. So you have to come up with a fixturing method of holding the part so that you can adequately machine all the features that you need to machine. And even something as simple as understanding you can create toolpath as the programmer, but you need to understand the part design and coming back to referencing your datums. And, where are those dimensions coming from and what is most critical when you talk about particularly like prismatic machining and their relationships to holes and surfaces and things like that, that you have to reference those points when you're doing your work shifts and your fixture locations.
Now, you've mentioned fixturing 3 times, and have not even asked the question about fixturing. So let's get into it. Yeah, obviously, fixturing and work holding is very important. But what advice would you give to someone who is generating tool paths? Do they have to come up with a fixturing at the same time that they generate the program?
Well, actually, and again, this is one of the things that unfortunately, and you're getting into your larger companies and stuff where they're doing larger volumes of parts in the cases, is a lot of times they're individual people. The programmer writes the program, and a designer designs a fixture, and a different designer designs a part. And in reality, if you go back 30, 40, 50 years ago, all of that was one person. He would sit down and he would basically process the whole part, so he had the experience to all levels. Now you've got to have people that are very proficient in maybe a fixture design or in a toolpath generation, but they may not truly understand cutting tools. And it's kind of crazy. I'm a tool and die maker by trade, going back a long time ago, that the simple 1, 2, 3 concept of fixture design, that you have to make sure that your supports for your part and your clamps are over top of your supports, so you're not distorting the part through the clamping process. As you mentioned earlier, a lot of the parts you're seeing today are a lot more sophisticated, and that makes it a lot more challenging to be able to hold the part and clamp it so that you can then machine it. Because if you're not holding the part securely, or the design of the part is rather complex, then your machining process and your tool selection has to be compromised to whatever, as the old saying goes, the chain is only as strong as its weakest link. So you have to figure out what that weakest link is. Is it the part, your ability to hold the part, and then they can start going about machining the part.
In practice, do people buy, like work holding? I know there's general purpose work holding, and then of course there's special purpose fixturing for individual parts. But in practice, do people work on that first, or purchase work holding first and then put in the other pieces to create a part?
Well, again, the correct or let's say the most efficient way of going
Most
about that
efficient.
literally is to have somebody I'll call it a process engineer. And that process engineer says, okay, here's the part that I have to do. Okay, here's my ability to hold the part. And then he can take that information and say, okay, to the programmer, here's the part, here's how it's held. Now, and I need to machine these features on it. You need to give me the tool path to be able to generate those features.
I do a lot of work in a lot of reporting on additive manufacturing. And surprisingly to me, perhaps not surprisingly to you, but surprisingly to me, a lot of the work that people are finding practical use today is using additive manufacturing for fixturing. Are you seeing the same thing? And is that impacting how you're providing tools to your customers?
Well, and again, that's one of the things that follows the same thing we talked about in general is that the experience level, a lot of companies through the course of economic shifts and stuff within their industry, if you went back into the 80s and 90s, a lot of your companies had apprenticeship programs. And those apprenticeship programs could be geared towards designing, running machines, programming. And because of just economic conditions and changes in business philosophy, a lot of companies have gotten away from their apprenticeship programs, and they rely on outside institutions like the colleges. Well, unfortunately, a lot of times, a lot of the people that are maybe very good teachers never actually had practical application. And again, like we said earlier, that sometimes the theory and practical application don't always agree.
That's true. That's true. So let's talk about machines. And maybe we can talk about machines and then get back into fixturing as they apply. But machines today seem to be getting more powerful, cheaper to use, faster. There's things like high-speed machining that's become the norm. What sort of advice would you like to give my listeners about machining today when it comes to the machines?
Well, the simplest thing, first and foremost, is the machine has to have enough of a machining envelope to machine the part you're going to hold. That's probably the first thing to think in terms of I've got several customers who all of a sudden look at a job and they bid it and they get it and then they realize it doesn't fit into the machines they have. So that creates a problem in trying to machine part of it and then move the part and then machine some more of it. That's one thing, and that's an easy one. It's kind of, again, goes back to the experience thing, much like you talked about. The new technology in machines, a lot of the technology is geared towards speed. And high speed or high feed machining can make the machine move faster. But the reality of it is when you start doing this, you have to understand a lot of the machines today are all AC motor machines. And what they want to do is they want to change tools real fast. So you've got a machine that might have a 10 or 15,000 RPM spindle, and they put a big horsepower motor on it so that they can very quickly accelerate to get up to the spindle speed so they can get in cut. But what they fail to take into consideration is what the horsepower machining curve, because ultimately, after they've changed the tool, what they want to do is start cutting. And that understanding of how that RPM torque curve, horsepower curve, relates to the size of tools. And that's something that very commonly happens if somebody thinks that they think that if they get a 15 or 20,000 RPM spindle machine, that it's going to be a lot faster. Well, that's true if you're using real small diameter end mills, but if you're using 2, 3, and 4-inch face mills, you're going to be cutting down maybe sometimes under 1,000 RPMs, and your machine has to have enough power at that RPM range to be able to do the machining and metal removal rate that you want to do. And that's one of the things that really happens all too often is people don't understand this horsepower curve when they're buying a new machine, and faster by spindle speed and all the rapid travel rates and things they talk about may not be the key point. Your ultimate thing with the machine is you're going to try and machine material away with it. So you have to understand what size tools you're going to use, what kind of RPMs you're going to be running, and therefore to make sure that machine has power in the RPM range where you're going to run it at. An awful lot of the times today, customers already purchased the machine and he's got it in there and he's not happy with the way it's cutting. And a lot of times the answer is you have to downsize, go to a smaller diameter tool to get the RPMs up so he has the adequate horsepower to do machining.
So there is a way for you as a tool maker or tool provider to help ameliorate problems with perhaps less than ideal selection. Let's put it that way to be charitable. Less than ideal selection in the machining. but they're not optimal.
Right. And again, everything about the machining process is a compromise. And the compromise goes back to the comment I made about the chain only being as strong as the weakest link. You have to figure out where the weakest link is. Is it the tool? That's what we would like it to be. But is it the machine and where the horsepower is? Is it your part and its configuration and your ability to hold it and fixture it? You have to take all those keys into effect. And then, again, the key point is what's that part made out of, and to match it with the right type of cutting tool material so that you've got the right speeds and feeds to give you the end result of an efficient machining cycle.
You just said a very interesting point, which I think is obvious to you, but maybe not so obvious to me and my listeners. You want the weakest link to be in the tool, in the cutting tool.
Correct.
Can you expand on that?
That's the most perishable item, and that's the item you're going to replace all the time.
Oh,
Yeah. So, I mean, that's ideally,
right.
you would like it to be the tool being the limiting factor. And then there's always, if you look at the transition of technology, if you go back into the 50s and early 60s, you were talking about high-speed steel tools. And then they got into carbide tools, and then they got into coated carbide tools, and then they got into ceramets and ceramics and CBN and PCD. All of those cutting tool materials are designed to work in certain kind of materials under certain cutting conditions. And the key becomes, what is your material? What different cutting tool material will work efficiently on it, and then at what cutting speeds?
Interesting. So let's for a moment, let's just take that knowledge, just take that and put a pin in it and circle back to the programmer figuring out the tool paths. Do they consider the fact that the kind of tool that you're using when they create those tool paths, or is it strictly mathematical? And if they don't, should they?
Unfortunately, in a lot of cases, they don't. And it goes back to the comment about the experience level of the various people involved in the process. The programmer is very good at making decisions, but he may look at the part and say, okay, I got a work surface there that's 3 inches wide, so I need a 3 or a 4 inch cutter to cover that surface. Well, once he's decided that that's going to be the size tool he needs to cover the surface, then the next question is my fixture strong enough that I can use and take that big of a cut at one time? And will my machine have enough power based on the amount of material that has to come off it to do that operation? So again, it's a whole picture of looking at things.
Clearly, there are things that your customers could do to integrate that knowledge. But before I ask that question, are there things that Ceratizit could do to integrate that knowledge? Are you working with, say, the CAD/CAM developers to import your tool knowledge into their systems?
Well, we are. The hard part has really been magnified over the last couple of years with COVID and the ability to interface with people. And much like we're doing this interview via the internet and a podcast, that is what become a new challenge today, is to relate information to customers and to other technologies, to share technology. Because again, much like we talk about the machining process, a software developer is very good at developing the software. A tooling developer is very good at developing the cutting tool. And somehow then we got to relate that into the machine tool and kind of get everybody on the same page. And typically a tool builder is a tool builder. A machine builder is a machine builder. A CAD/CAM system, the builder is a CAD/CAM system builder, and they aren't all necessarily intertwined to each other.
Right, but they could be. I mean, you have data. I mean, a program, any kind of computing program works on data, and you would have data to provide them.
Correct.
Right. Yeah. So, just curious.
And that's kind of what an awful lot of my job is to work with the customer who has to machine the part and try and, where possible, because a lot of times his knowledge level is based on his experience level. And you talk about a CAM system that's going to do the programming, there are a lot of features that are new capabilities that are coming out all the time to increase capability, but he may be working with an older CAD system that doesn't have some of the features that are available. Something as simple like in milling today, something that's becoming more popular is trochoidal milling. But if his CAM system is an older one and doesn't have that feature on it, he would need to upgrade his CAM system to be able to do the newer technology, which again goes something that's more and more of the newer high-speed machines. They're using a smaller diameter tool, using this trochoidal milling process, which is a whole different process of how you do your toolpath generation than when you used to do just a straight line XYZ kind of move patterns.
Right. Right. I mean, it's a more efficient way of doing things. It's a better way of doing things.
particularly if you're dealing with a complicated part or a part that's has some limitations on how you can hold it. You have to reduce the cutting forces, and one way you can reduce the cutting forces is to take more, faster, lighter cuts. Instead of an older technology as you had these great big, huge, high horsepower, really rugged machines, and you took big depths of cuts real slow. Today's technology, you're using smaller, lighter, faster cuts. At the end of the day, particularly if you're doing prototype parts, that's an easy way because you don't have to have a sophisticated fixture to hold the part. You just back off all your cutting parameters to the ability of your ability to hold the part.
So those lighter, faster cuts also, I imagine it makes that chip control a little bit easier too.
Actually, sometimes yes and sometimes no. Actually, controlling the chip sometimes can be a problem. Typically not so much in a milling operation because you have multiple teeth and you're in and out of the cut. So just by the machining process, you're getting chip control. When you talk about drilling and turning, that becomes a little bit more of a problem because it's more of a continuous cut. But in a milling process, because you got multiple teeth cutting, normally chip control isn't as much of a problem as moving the chip so it's out of the cutting zone and not recutting the chip. That creates more of a problem in the milling process than actually creating the chip. It's making sure the chip goes where you want it to. And then one thing we haven't really talked at all about, but becomes another feature in there, depending upon the material you're machining and your machine, is coolant. And you think of the factor of what coolant brings to the mix. Coolant does do what it says. Its main factor is to cool the cutting zone, and that would allow you to run faster, give your tool longer tool life, but can also become the vehicle that moves the chip out of the way so you're not recutting the chip.
Interesting. And I'm sure there's different ways of handling coolant that you as a tool provider can provide.
Well, when we talk indexable tools today, almost all of our indexable milling cutters today have a channel through the body of the tool coming down to where the insert pocket is that would allow, whether using air, minimum quantity lubrication, or flood coolant to come through and help wash and move the chip out of the way as well as bring the temperature down. In ground tools, it's not as common because typically there you have to rely on either flood coolant or blown air to get in and lubricate and help move the chip out of the way. But that's all part of the process. And that's, as you mentioned, that's a good key point sometimes is that once you've created the chip to get it to go where you want it to go, so it's not going to interfere with more of the machining process.
So let's talk about the customer. I mean, clearly that's a large part of what Chuck does is talk with customers and deal with their problems. What are some of the trends that you're seeing right now, either before COVID or during COVID, that you think are really impacting the business, and some advice you might want to give our listeners to deal with those challenges?
Well, a lot of what the issues are out there was one of the other points I mentioned is through the course of COVID, a lot of companies slowed down in their business. And in doing that, they did some level of downsizing, whether they did it by furloughing or encouraging people who are of retirement age to retire, things along that line. But what they did is they lost experience. So now as things are picking back up again, the idea becomes a matter of trying to find somebody who has the experience level to get in to do the job that needs to be done. Now, again, a lot of businesses are picking up, and the idea becoming, how do we do more with less? So the guy who maybe used to be just a programmer now is being asked to go on the shop floor and become the on-floor tool engineer to help troubleshoot problems and things like this. And he may not have the experience today, so he may call somebody like myself in and say, here's my machining process. Here's some of the issues we're having. What can we do to minimize or eliminate these machining problems that we're having? And that's really what my job is.
Right. And it sounds like a very important one nowadays. So I think one of the key things I've been hearing from you and from others outside of this podcast is what you might call knowledge integration, trying to get people from these different stovepipes. And it's easy for companies to get stovepipe because it's hard to learn these CAD/CAM programs. No matter, I mean, they're making them easier and easier to use, but nevertheless, it still requires some expertise, to go ahead and create a tool path to the point where they might just get swallowed up in that, and then they're ignoring going out on the shop floor, not doing the things that they need to do to understand the process from a practical point of view. So I think that's one piece of advice you might want to give our listeners, if you would agree with me.
Oh, absolutely. I think the key becomes a matter of trying to understand that whole process. And again, keeping in mind at all times, the objective is you have to make the part to print, first of all. And then you want to make it as efficiently as possible. And so then you kind of keep, working your way back into the process of where are my issues? Is my issues with tolerance? Is my issues with being able to maintain a surface finish? Is my problem is I just need to do more parts faster? And then you start looking at where is that weak link we talk about and to try and make it most efficient as possible. And sometimes when you talk about some of the sophisticated parts and materials that are out there today, sometimes it's hard to convince the customer that this is as good as it's going to get. That's where technology is today. And you just have to realize that this is it. I mean, we've only got cutting tool materials that are going to be able to run so fast in this material. And as much as you may want to go faster, you can't. This is where you're going to go unless you're just going to burn up tools and then spend more time changing tools than doing machining.
Physics has its limits.
Yes, it does.
Interesting. So let's, before we're getting close to the end here, let's talk about cutters, inserts, geometry, and grade. We haven't really talked about the tools themselves. Are there new developments or things that you think that our listeners really should be aware of and need to know about when it comes to the cutting tools themselves? I mean, you have such a broad variety of things that could be an open-ended question. We could sit here for 3 hours, but I'm sure.
Oh, we could spend a lot more time than 3 hours on it. The key then goes back a lot of times to the configuration of the part. The cutting tool has to generate the form of the part. You can't have bigger lead angles than what the configuration of your part is. So therefore, you have to go through and make sure you have the right lead angles and geometry of the tool to match into your part envelope that you're going to machine. The people in the tooling industry all make good cutting tools. The question is a matter of correctly applying the product that you have to the application that you have. And that's probably one of the things that run across most often is a customer is using a tool that he has in his shop today to machine the part that he's trying to machine tomorrow. And a lot of times that's not the right tool. Again, you go back to what we talked about early on. What is the material you're going to machine? Is it something that would lend itself to using a coated carbide tool? And if that's the case, is that coated carbide tool one that would be CVD coated or PVD coated? Is it something that could be a Ceramet? Could it be ceramic? Could it be PCD? Could it be CBN? These are all things that come into play in determining how you're going to go about machining that. And again, the tool that needs to be able to fit in there, and what I oftentimes refer to as the cutting edge. You have to understand coming all the way down to where the geometry of the tool meets the part. And when you talk about a ground tool, by example, it's going to have a very sharp cutting edge. As you go to indexable tooling, typically because you're going to be handling it more, that tool is not going to be as sharp as a ground tool, and therefore will take a little bit more cutting pressure to cut. And you need to understand all of those different features when you're in there is what's the geometry on the tool, how sharp is that tool, what kind of feed rates can I subject that cutting tool to based on the strength of cutting edge? And then obviously, based on what that tool is made out of and the material I'm going to machine, what kind of cutting speed can I subject it to have a successful operation?
Wow. It sounds more art than science. Would you agree with that statement?
Well, and again, there is a level of truth to it, and that's why typically a lot of the machining people that are out there are called craftsmen. It's no different than a carpenter who knows how to do fine carpentry versus a guy who's a framer. Okay, the same thing is true in the machining industry. You've got the guys that are good at rough machining, but then you've got your really highly skilled people that do the finish machining, because a lot of the tolerances and stuff that are being asked to be done to today are what used to have to be ground. And we now have machine tools that are accurate enough and repeatable enough and tooling that is durable enough that we can actually replace an awful lot of what used to be grinding operations, both by finish and tolerance, by controlling the tool path, the amount of stock remove, and the cutting speeds and feeds.
Wow. It still seems like a PhD on itself, perhaps even more than that.
Well, and again, a lot of the things even that we talk about today is something that more and more shops are getting into is what's called hard machining, where you take a part that used to be, you'd heat treat it to 45, 50, 60 degree Rockwell, and then grind it. Mm-hmm. And today we can do that with carbide cutting tools or CBN or some other material, depending upon the application and the style and fit of the tool. And then the coatings. There's a lot of things that we do is we take a carbide ground tool and we apply different coating materials to it that can give us the characteristics of it being a harder tool than what it is.
Interesting. So we promised our listeners that we're going to talk about 6 keys to a successful milling application. I think we talked about those 6 important things and possibly more, possibly even 7. But can we summarize for our listeners real quickly of what you think are the 6 key things they need to worry about to come up with a successful milling application?
The first thing is understanding your part. You have to make the part to print. So that's one. Okay. The second thing is understanding your ability to hold and fixture that part to be able to machine it. The third thing would be understanding your machine tool so that you can accurately go about doing the machining process efficiently. The fourth thing that would come to the programmer to know how to generate the tool path to be able to do that. The other thing is that there's another scenario that I use a lot. It's if it sounds good and if it feels good and if it looks good, it probably is good. And that is the analysis of the application when you're actually doing it. We can go through and we can do all those first 4 stages, but now it comes to the reality of when you go to the shop floor and start analyzing everything that you engineered. Is it working the way you engineered it? Because you have to make adjustments. Everything is making adjustments to that weakest link. And then again, we come into making those adjustments, understanding the wear pattern of what's happening to the tool, making sure that you selected the right cutting tool, the right geometry, the right grades, the right cutting speeds. And then lastly, the applying of coolant or air to the part to be able to machine it. So I think that's looking at the whole situation
Right.
when we talk about the ways of going about it and to actually use that level of a methodical approach to it. In a lot of cases, there's another old saying out there, and I'm big on cliches and old sayings, is you can't see the forest for the trees. And sometimes somebody is looking at something so closely that they're not really seeing what the issue is. They need to stand back away from it a little bit and see what's really happening. Am I getting a finish problem? If I'm getting a finish problem, what's causing the finish problem? Can I not hold my dimensional tolerance? Why can't I hold my dimensional tolerances? These are all things that will factor in the part configuration, my tool path that's being generated, the rigidity of my setup of how I can hold the part, and the ability of my machine to be able to do the machining process and repeat it time and time again.
And with the number 5 is finding the right cutter or insert, and number 6 is making sure you're using the right cutting parameters, the right speeds and feeds.
Correct.
Yeah, interesting.
Yes.
And then number 7, which gets back into all of this and plus other things that you said, is invest in your people and make sure that they understand the whole process, not just individual parts of it.
Understanding the whole process. And one of the things that you kind of we talked about earlier was the idea of integration, all the ideas.
Right.
One of the things is things have slowed down through COVID and just in the general manufacturing philosophy over the last 10 to 15 years is training. You have to train everybody. You have to train the programmer. You have to train the machine operator. You have to train the setup person. You have to train the management people to have a better understanding. They cannot manage what they don't understand.
Right. So more knowledge is better.
Knowledge. And that's a lot of what I do also. I do a tremendous amount of training and a lot of it is based on with the process people and the operators because they are the ones that can take whatever the engineering and the management people have put out there and basically edit it or adjust it to deal with whatever their weakest link is.
Right. Fascinating. Well, we can talk more, and maybe that'll be for a future conversation, but I think that's all the time we have for today. If our listeners want to learn anything more about Ceratizit, where on the web should they go?
Well, there's a real nice website called ceratizit.com, and obviously to contact us through the 800 number there or the website. And then there's a group of people like myself that you contact us, so we're more than happy to reach out to the customers and talk specifically about their applications, because that's really where it comes in, is that every machining application is different. And that's where a lot of cases is for us with the knowledge that we go out and see a lot of different applications in a lot of different environments to take the knowledge level we've attained and share that with our customers.
Sure. Again, knowledge transfer.
Knowledge transfer.
And thank you to our listeners for listening to this podcast. As always, SME and SME Media can help you keep abreast of developments in automation, robotics, and smart manufacturing on our website, sme.org/latest-news. For our library of podcasts, go to sme.org/smemedia/podcast or look for Advanced Manufacturing Now in your smartphone's podcast link or wherever you find your podcasts. Thanks again for joining us.